Hello everyone, welcome back to KY Tech. And today we're going to have a brief introduction for the semiconductor, including the whole industry from the design, fabricate, and also the packages. And also we'll talk about the basic unit for the chips, which is the MOSFET, and how does it work, and some basic introductions. Then also we'll go into an overview process to how to fabricate the MOSFET. And we have a series of video about talking different techniques for the process like lithography, like diffusions, like etchings, and you can check it on this channel also. So first we can see on the right hand side it's a NMOS. So if you're not really familiar with the MOS, we'll have a introduction later. As usual, we will have a brief one-page overview first. So first is a IC industry. So we'll have companies like Tesla or Microsoft or HP. They want to have a specific chips. And for example, they want to use it on the phone, on the PC with different features. So they'll give all the spec. Then it will send it to IC designer, which Qualcomm, AMD, Nvidia, they are really good at designing the chips, and most of them are fabless, so they don't fabricate; they just design. They have digital and analog designs. Then they'll start, for example, like for digital, they'll start using behavior code like Verilog to write all the logic and the architecture design first, and the logic design. Then it will compile to a gate level. Then they can use software to make it to the circuit level, so the circuit design. And also after that will be physical design. In the middle, they'll have a verification engineer to verificate the functions and the logic. After that, they'll start doing the layout. Then they'll check the LVS, layout versus schematic, and DRC, design road check, to measure the layout was met with the PDK for that foundry provide, and they'll keep doing a lot of verification and test. After everything was done, they'll send it to foundry, so they'll provide GDS file. So from the upstream to design house, sometimes it will be the same company, like Nvidia. They have their, or Tesla. Tesla will have their own needed for chips, so they will design by themselves, or Intel. After that, they send to fabrications. So based on the GDS file and based on layout, we have different masks to fabricate a chip by lithography, by etchings, by diffusions. So in here, company will be like TSMC, Global Foundry, Intel, Micron, and then they send it to packaging, which originally what they want to do is to protect the chips from moisture, from temperature, from humans. But now they are turning to more things on it because we're reaching the limit for MOS though. When we keep reducing the length for the MOSFET, they figure out they can start working on packaging to improve the throughput to reduce the latency. So for packaging, it will be like they have a PCB. Then there are something called interposer. In the interposer, we have a C4 pump and RDL. Then we have TSV through silicon vias. Then RDL again. Then pump. And this whole part is interposer. After that, we'll have chips like CPU, then HBM. So they package it into one on one interposer, so we can have better throughput and smaller latency. Company include Amkor, ASE, and also there's some company that can do from design to fabricate, then to packaging. We call it IDM. Intel is one of them. After that, we got chip. Then we go to the PCB design and go to system. Then eventually we'll have application on this chip. So that's the whole industry. Then we'll go through the basic unit MOS. So here we can see we got a MOSFET. Here we have a source, drain, and this green one is a gate. So for NMOS, for example, we'll apply voltage to the gate, and we have a voltage threshold. If voltage on the gate is larger than voltage threshold, we can turn on the MOS. And also VDS, if VDS is larger than VGS minus VTH, which we call it V overdrive, it will be in the saturation regions. And we'll talk a lot of more detail in the later slide. Here's only a brief overview. So at this situation, there will be a current flows from drain to source. So electric will move from source to drain, and it's in the saturation regions. So what happens over here? Originally, we have a gate, and we dope N-type element into a silicon, like phosphor. So here will be more electron, more negative. If we don't have we only apply a little bit of VG, probably nothing happen. But if we start increasing the VG, we will saw a depletion there. And if we increase more to make it larger than VTH, we will see a depletion there, which is negative over here. Then the electron can flow from source to drain. So MOS is like a button. We can use a VG to control it on the off, and based on this logic, we can create a lot of different logic on the chip. So we're saying there's a current from drain to source, but how large is the current? It will be on this one. So we have ID equal to mobility. So we have hole, and also we have electron. So it depends on which, that is NMOS or PMOS. And electron move faster than hole. We have C oxide, the oxide capacitance, because we know MOS is metal, oxide, semiconductor. So we have a metal, then we have an oxide below, then it's a semiconductor. And also we can play around for the VTH over here. We can change the oxide, or we can change a metal to tune it. Then we will have a width, which is this part of a MOS, and we have length, which is this part. So it will be like this part is the length. So from here we can see we want to keep shrinking the length, so we can have higher current. Higher currents means the device will be moving faster. However, if we keep reducing the length over here, we will see they're possible to have a leakage and also a power consumption. Then it's VGS minus VTH square, and theoretically the equation will be only over here, but in reality we will have this channel length modulations. So in long channel, lambda is corresponding to L over 1. Here is a L over here. So if it's a long channel, lambda will be 0. Then there's nothing have effect on the channel length modulations. But if the length keep shrinking, then we'll see that VDS, if we increase the VDS, we'll increase the current for a little bit. So we'll see a plot like this. Here's VDS, and here's I. We'll see directly it should be like this. Here's a saturation region, here's a linear region. But in reality, we'll see it become higher based on VDS. So we can see there's a couple factors can change the ID. First is a VGS. Second, you can reduce a VTH by tuning the metal and oxide while you're doing the while you're just etch out the poly gate and fill in the gate material. Also, you can tune width, you can tune length. You want the length as small as possible. And so once we have keep reducing the length, we'll reach a limit, which if we keep reducing it, we'll have a leakage issue. Then here's a time they use FinFET. In here, we increase the active area, which is yellow one. So originally width will be like this, but now the width we have a 3-dimensional, so width will be 2 fin height plus 1 fin width for the width. So we can largely increase the current without keep reducing the length to prevent any leakage. So that's a basic overview for the MOS, and we'll talk really much more detail in the later slide. Then it's a process. How do we fabricate the chips? This is only an overview, but there will be more detail later. So first, we need to, here we call OD. So we implement the N well and P well region. Then we start making the fin. So by this way, we put a lithography and we put etchings to etch out the fin over here. Then we use the VD to fill with STI. So that's to isolate that different device. And then we start using pH and lithography and also the etchings to have here we call it poly. That's a gate, but it's not real metal. So far we just have to make a poly gate to define the first the gate and how high this is. Then they etch the fin and grows an epoch over here. So current method they don't do implementation is because we're shrinking the length of a MOSFET. If we do implementation to make this silicon to become N+, there's possible it will be over implemented and here will be cause a leakage. And also for the epoch, it can have better higher concentration for that. After growing the epoch, so epoch is trying to grow the drain and source area. Then they start to do the replace metal gate, so RMG. So in here they etch down the poly gate and then they fill up the metal they wanted. So in here they will first fill the dielectric area, then put on the metal by keep doing the photolithography, etchings, filling, and etc. So let's go into the detail. So first we can see for the whole semiconductor industry, we'll have companies like Microsoft, HP, Tesla, or Google. They want to have specific function on the chip, so they'll give us spec to the fabless designer. In here, AMD, Qualcomm, Intel. They'll start designing the chip. So for designing the chip, what they will do, they get a spec, they do architecture design first, then they start doing the logic design by, if that's a digital, they will do the Verilog, and we'll have an example later. After that, they will compile the code to gate level, and then probably in cadence, we'll say a real circuit, then they do a layout. And after layout, they'll start testing a lot of things, like they'll also have verification engineer to test the logic in the behavior level. Then they will check the LVS, layout versus schematic, and DRC to make sure all the layout was following the PDK rules provided by Foundry, because there are limits on each process, so we don't want to violate those rules. And after they figure out like everything was good, logic is good, then they send a GDS file to fabrications, which is Foundry. So in here, sometimes the company will be the same, like Tesla, they have their own edit, and also they design their chip by themselves. And also Google having the same issue. Google will do the same thing now. Then they send out to fabrications, which is Foundry, TSMC, and Global Foundry, SMIC, or Intel. So they fabricate a chip based on the mask, based on the layout, then do a lithography, then they do the etchings, diffusion, and keep doing those steps to fabricate out the chips. Then after that, they send those chips to packaging and testing. And in here, originally, those packaging was trying to avoid the moisture, the heat, the human breaking the chips. But now they're trying to do is to based on the packaging to improve the throughput and reduce the latency. So how does that work? We'll have an interposer over here, and in the interposer, and here's a PCB. We have C4 pump, we have RDL, and we have TSV, and RDL again, then C2 pump, then we'll have CPU and HBM. So we'll see it's really close for the CPU and the HBM. We're packaging on one chip, so we can improve the throughput and reduce the latency to make the device faster. So for packaging, Amkor and AS is really good at packaging, but now even Foundry, they do advanced packaging by themselves, like TSMC, they have CoWoS, and also Intel are working on it. And some company will do from design to fabricate, like all by themselves, like Micron, and also Intel. So here we call it IDM. They design the chip, they fabricate the chip, they package the chip by all by themselves. Then after that, we'll get the chip, put in the PCB design, put into a system, then we have application on the chips. So besides design house, besides foundry, besides packagings, also there's some company will be very interesting. First is EDA. So remember we mentioned during the design, we'll have during the layout or in the analog design, we'll use all of their tools by Cadence. So they provide a software for us to design the chips and doing the layout. Also, we'll have equipment supplier like them, KLA, Apply, or ASM for their EUV, provide the tools for them for foundry or for the advanced packaging to make out their chips. So that's going to detail how do we from design to fabricate. In here we have behavior language like Verilog. So design house they write Verilog, which they have input A, input B, and output Y. Assign Y equals A and B and a NOT. So they want to make a NAND gate. So what does NAND gate mean over here? We can see from this table we have A, B, and Y. So if we give A input 0, Y input 0, we want to have it as 1. If we because A and B equals to 0, but we give it a NOT, so it will be equal 1. And if A equals to 1, B equals to 1, we give first AND will be 0, and NOT again, it will be 1 again, and etc. etc. So for the MOSFET, for NMOS over here, we'll assume if we give it 1, we can turn on MOSFET. If we give it 0, we'll turn off. If we give PMOS 1, it will turn on. If we give it 0, it will turn on. Give it 1, it will turn off. Then how does it work? So we have behavior level. It will compile to the gate level. Then it will then compile to the circuit. So in the circuit, here's a circuit we have 4 MOSFET, 2 NMOS, and 2 PMOS. So next is if A equals to 1, B equals to 0, what happened? T3 will be open, and also T2 will be open, but rest of them will be closed. So we'll see the current will, the VDD will from here to the output, so the result will be 1. However, if we give both of them 1, what happens is 2 PMOS will be closed, but 2 NMOS will be on. So the voltage will be drained down to the ground, so output will be 0. So you can play around, you'll figure out that this circuit is really the gate over here, the truth table over here. After we have the circuit, then we do a layout. So in here we can see we got 2 PMOS over here, 2 NMOS over here, and we have a VDD, and we have a GND. Here's the bulk. We'll talk about it later. Then we got output. So based on this, we have different layers of the chip, as we can see over here. Then that's a GDS2 files. Based on the chip, Foundry can start doing the lithography based on the chip, and then etch away, then deposit one by one to make out the circuit. So in here, we'll see here's a basic layout over here. We can see here's a VDD, and we can see here's a GND for a metal 1, and we have metal 0 to connect all the FinFET. and here's a gate. So that's how they do from design, compile to circuit, then draw the layout out. So based on this, it will be a different map. So the foundry can start making the chips by the layout. Next, we're going to talk about MOS in really details. So what is MOS? Metal oxide semiconductor. So we got metal over here, we got oxide over here, and we got semiconductor below. So here's silicon. So normally silicon was 4 plus. So we're doping some different group of atom like phosphor, which is group 5, boron, group 3. So phosphor will have an extra electron if we dope into the silicon, and boron will have a missing electron, which is hole in the if we dope into the silicon. And what do we need it? It's because in here we have this is we call CMOS, and here it's an NMOS with a PMOS. So NMOS PMOS was really similar, but they do it oppositely. Here's how we draw NMOS, and here's how we draw PMOS. So in NMOS, drain will flow from electric current will flow from drain to source, and PMOS will be source to drain. So it's almost similar. So let's focus on NMOS first. So for NMOS, in here we'll dope phosphor in those region, which we'll probably do an implementation or epic. Then they will apply a voltage on it. So when we apply a voltage, originally we have a voltage threshold VTH. So if VG, which is voltage on the gate, is larger than VTH, the device will be on. But how? So originally, here's a device. We have N plus over here, means that we have extra electron. If we apply a little voltage over here, probably nothing happen. If we keep increasing, we will get a depletion layer. Then if we keep increasing a lot, electron will be attracted to this position. We got inversion layers. Then the electron can be flow from source to drain. So we create a current over here. So MOS is how we create it's like a bottom. So if we take a look at previous pictures, in here NMOS, we control the gate to make it on or off. Then we can have a different logic. Same with here. So also we got a bulk over here. So what is bulk? So that says here's a P substrate, here's an N substrate. Here we will have a diode. And in here, if for some reason here will be grounded to 0, but for some reason if here will be positive, then we will see a current flows from here, electron flows from here to here. But that's not what we want. The only thing we want is electron flow from here to here. This will cause a device issue. So we have a bulk and make it grounded. So measures here will be 0, and nothing happens to electron flow between this area. Okay, so that's the basic for the MOS. Then we'll look into the detail. By the way, here's a length for the MOS, and here's a width to the MOS. Okay, let's look into the detail. So as I mentioned, if we have a lower VG, nothing happen. If we start increasing the VG, but it's still smaller than VTH, we'll have a depletion region. If we keep increasing the VG, we'll have an inversion region over here. So the current equation for the MOSFET will be ID equals mobility, which is electron. We have two mobility for the NMOS and the PMOS. And for the NMOS mobility, that's an electron. It will be faster than the PMOS, which is a holes. C oxide. This is the place we can tune around for the VTH also. So we can change a dielectric material. We can change a metal gate material to make the VTH different. And here's a capacitance for the on-side. Then we have the width, as we mentioned earlier in this page. This is a width of the MOS and also a length. So we want the length becomes as small as possible. Yeah, over here. So if if we keep drinking, we can imagine the current will be larger, and we'll imagine the faster device will be faster. But they will be having the issue if we keep drinking this dance. These two will be really close together, and there's possible to call the current leakage and the power consumption. Then we got VGS minus VTH, which we call V overdrive over here. And this is an ideal equation, but we'll add on channel dance modulation over here when we keep drinking the dance. So lambda is corresponding to L over 1. So if we have a really large dance, means like the MOSFET over here, the dance is really large, lambda will be 0, so we'll go back to this equation only. But if we keep drinking the dance, then here VDS will play in a role. It will affect the current. So we can see on this area, VDS plot with ID. Here's a linear region, which is VG is larger than VTH. But VDS is smaller than V overdrive. So in this equation, that's for saturation, which means VDS is larger than V overdrive. Okay, so after it reached the this where is VDS equals to V overdrive, and we keep increasing the VDS, we'll see it going to saturation region. And if we count into actual reality, if the dance of a MOS is very small, we can see VDS will slightly increase the current. That's where this plays into the roles. And also, if we keep increasing VGS from here to here, we can see a current increase based on the equation over here. And here is the plot for VGS to ID. So we can see originally here's a cutoff region, which is this part. There's nothing happen. And if we start increasing the VGS, we'll see it going to the saturation region. How we know it's saturation region? So let's assume here is a part for VTH, part 1.3. Then we know that here VGS 3, so it's larger than 1.3. So it either is in linear or it's in cutoff. So in here, if we assume VDS is 3, and V overdrive will be VGS 3 minus VTH. So VDS is larger than that, so we know that it's in the saturation regions. So that's a basic for the MOS. And more details for the MOS. So we see we have cutoff region, VGS smaller than VTH, current is almost to 0. Linear region, VGS is larger than VTH, but VDS is smaller than V overdrive. And that is the one we're focusing on more. It's VGS larger than VTH, but VDS is also larger than V overdrive. So here's a direct the general equations without counting to the channel dance modulations. And here's how we draw the MOSFET. We got drain, we got gate, we got source. Here's a VGS, here's a VDS, and current will flow from the drain to the source. And here's an arrow showing that drain to source. Then there's another concept, is the short channel effect. So as we mentioned, if we keep reducing the dance for the MOS, current will be increased, but we have leakage issue and better worse consumption for the current. But besides that, there's still other effect under the MOS, and there's a couple. This is only one of them, which is the short channel effect. And in here, we'll need to add the equations over here that, like how we said previously, to modify the current. And there's something really interesting is here we got a pinch off, right? We can see here's pinch off. Pinch off is the when it happens when the current was in the saturations. So in here we can see VG to the V channel, which we call VC, will not always be the same. So in here, this VGVC will be really small because we have a drain over here with high voltage, and it will be VG equal in here VG and VC will be really small, which almost to VT edge, which here it can maintain the saturation region anymore. But because the large electric fields over here, it can still pull the electron from the channel over here directly back to the drain, having the current. And that's part 1 for all of this introduction. So for there's one more page. So in here, based on what we know that the yellow one is FT area. We got drain, we got source, and we also got gate. So ideally, by the way, here's STI, sometimes it's SiO2 to isolate 2 different devices or different MOSFET. So ideally, we will apply a gate and apply voltage on the gate. Then we'll see the current flow from drain to source. So remember the equation over here? So if we keep tuning the length, which is the length over here, we can keep increasing the current. But there's a limitations on the process. If we keep increasing, we'll see a lot of leakage. So another way is change the width. So that's what they're doing right now for the FinFET. They make the fin higher. This is a fin. So width now will be 2 fin height plus 1 fin width. Okay. So in here, current will be increase a lot, and that's what TSMC Intel was doing right now. And by this way, we can increase the current without keep reducing the length. And fun fact is like, for example, you heard that TSMC they have N3. People used to think that N3 is here will be 3 nanometer, but it's not. It's just a commercial naming rules. Originally it is, but right until like 19 or 10 nanometers, then it's not going. Probably 19 or 20. After that, it's not following these rules anymore. So here's history. We have a planar, then we go to a fin to increase a width to increase a current. And in the future, near future, probably 1 or 2 years, we'll have see something like GAA. Here's a narrow ribbon. So here's a gate. And here's a FT area, drain, and source. We can see we keep increasing the surface for the width, so we can keep increasing the current. Yeah, so that's for part 1, and we'll probably have another video for part 2 to talk about all the process to make out the MOSFET. Yeah, thank you.